All right. The next talk will be on the Windows Restart Manager. I'm very happy to have Mathilde Venault, I probably butchered that, on stage. Let's welcome her.
Hi everyone, and thank you all for your interest in the Windows Restart Manager. This is a Windows component that has been running in our system since Windows Vista, and yet that hasn't been fully understood. So today our goal is to change this together. Wonderful, thanks. So my name is Mathilde, and in case my accent didn't betray me yet, I'm French, and I work as a security researcher for CrowdStrike. I like to share my research at conferences, and I had the pleasure to talk at Black Hat and Cocoon before, which I'm also now a review committee member. And outside of computer science, I used to be a volunteer firefighter, so it's always a source of great stories when people are fed up of me talking about Windows. But today we're going to first focus on the Windows Restart Manager. We'll begin with an introduction to understand how and why it has been implemented in Windows. We will dive into its internals to better understand how it works under the hood. We will see that it can be hijacked for malicious purposes, and using real-world example, we're going to see that it has been used to support ransomware encryption, and we will also see that it can be used to perform evasion and anti-analysis purposes. We will then briefly talk about how processes can protect themselves against this type of hijack, and conclude with some thoughts. So we've all been stealing codes from MSDN, and personally, one of the first pieces of code that I've stolen was a create file. All I wanted to do was access the content of a file, and I had no idea what were the expected arguments. So what I did was go to MSDN, steal the piece of code with the default way of opening a file, and without knowing it, I was accessing a file that was already existing with open existing, with a generic access read, generic read, sharing the access with file share read. And it's only a few years after that I realized what those arguments meant, and that I wonder what happens when you don't share the access on the file you're opening. Well, when you don't, if other processes attempt to access the file that you opened without the access, they would typically get this pop-up saying that they can't access the file as the resource is currently used and blocked by other processes. And if they really need to access the file, well, the most straightforward option for them is to restart the whole system, to force the processes to release the locks they have on the file. But this is clearly not a good option because it forces a whole reboot of the system and makes the user lose time, energy, and it's certainly not optimal. So this is to answer this exact problem that Microsoft introduced the Windows Restart Manager. Starting in Windows Vista, it has been introduced within the name RSTRT MGR DLL, and its whole goal is to avoid, or at least reduce, the number of reboots required during an update. Why updates? Because it's typically the case that we explained right before. The updaters or the installer will need to update files, and they really want to make sure that no other process will prevent them from doing so, because they can't afford to be interrupted in the middle of the operation. So to do that, they will provide application a way to priority update or the installation, check if a resource they need to access is currently blocked by other processes, and if it's the case, give them an option to ask the system to shut down the processes that are blocking the resource instead of doing a whole reboot. So to do that, application will communicate with the Restart Manager through what we call sessions. Sessions are the place where the application will communicate with the Restart Manager, sending and receiving information. Sessions will then contain the resources that the application needs to access. So it can be, as we described before, a file, but it can also be a process or a service. So the first step to do that is to create the session. So the application using the DLL will initiate the session. Then they will register one or more resources that they need. So it can be one file and one processes, many services and one file. It can be a set of them. And then the Restart Manager will do its work and return the list of what we call affected applications, which is the list of processes blocking the registered resources. So in our case, we register, let's say, one file, file X, and if an application called log file is blocking it, the restart manager will give us the name and information about this log file application that is blocking the file. To be able to perform that, the restart manager exports a bunch of functions, which the core ones are listed on the screen. So we'll begin with RM start session that initiates the restart manager session. Then applications will be able to register one or more resources using ARM register resources. Then they're going to use ARM getList to retrieve the list of affected applications. And then, if there are any, applications can ask the shutdown of those affected applications using ARM shutdown. For all the applications that have been terminated with ARM shutdown, the application that has started the restart manager session can also ask for a restart of them if they comply with certain requirements that we'll detail later. But what's really interesting is to understand how it works under the hood. So let's see for each of these functions how it works. ARM start session will begin assigning an ID for the session. The restart manager can handle a maximum amount of 64 sessions for the whole system, so you would get an ID between 0 and 63. Then, the restart manager will create an internal database. So the restart manager internally has a table with all the sessions that are currently open in the system, containing the information about the session. And it will initialize the same information in a hive. So under the user hive, we will retrieve for each session a hive with the ID of the session and the following information. The owner that has a PID, so the PID, the process ID of the process that has started the session, a file time corresponding to the time where this process has been started. We will see a number called sequence that represents the state of the current session. So a session can be currently started, but it can be currently shutting down application or restarting them. It's a number which can be from 0 to 4, depending on the state of the session. And also a session hash that corresponds to the identity of the application that has started the session, and also a unique ID that is given back in the arguments of ARM start session. Once this session has started, the application will use ARM register resources to register the resources in the internal database. So the restart manager will update the database it already initialized with this new information and synchronizes the information with the new registered resources in the hive of the session. So if we take the example that we had right before, we can see that we get two new values. So the name of the registered resources, in our case, the spooler service, and we'll get the hash corresponding to the identifier of this registered resource. Now let's move on to ARM getList. It's really important to understand that this function is the heart of the restart manager, as it's the one that retrieves the list of affected applications. And it's a really hard job to do, as affected applications won't be using a resource the same way depending on what is the nature of the resource. Indeed, a process does not use a file the same way as a service is using another service. So to be able to realize this hard job, it relies on what we call decorators. They are internal components, a set of structures and functions that are designed to collect a given type of information, and we can list two of them. There's the system information, which gathers information about what's happening in the system, and an application information. Once we identify a target affected application, those decorators will try to get information about this specific application. So for the system information, we can list the first decorator named sysprocinfo that retrieves the list of processes currently executing in the system, and similarly the svc info decorator that gathers information about services running in the system. But we also have a window info decorator that gets information about active graphic windows currently open in the session. So those three decorators will be updated at a regular frequency to make sure that they get live info about processes, services, and graphic windows currently in the session of the user. On the other hand, for the application information, we get a first decorator named signature info that for one given application will retrieve the specificities, so the full path, the file description, and so on and so forth. And also another one called the restart decorator, whose job is to determine for one given app if the app is shut down with ARM shutdown, will determine whether or not the application can be restarted afterwards. Indeed, to be able to be restarted with the restart manager, applications have to comply with certain requirements and register a callback and have some other specificities such as the restart command line, because if it's automatically restarted, the system really wants to make sure that they're not messing with certain parameters that may be required or certain specificities. So those 5 decorators will be the basis for the restart manager to determine the list of affected application. So once we're going to submit to the restart manager a register resource, so let's say not.txt, the restart manager will use those 5 decorators to determine what are the affected applications and be able to return the list to the application. But we have to understand that it's just a basis. They give the information. And what's really interesting is to see how it determines what are the affected applications depending on the type of the resource. So for files, under the hood, the restart manager uses the function anti-query information file with the ID file process ID using file information. And this function under the hoods iterates over all the processes of the system, retrieves the process handle table, which is a table containing the handles that the process has currently opened. And for each of them, it's going to compare whether or not the handle is on the registered file. And if it is, so the handle given here, and if it is, we'll check whether or not the access is blocking other accesses or just opening it. For services, it's a bit different. The restart manager will first retrieve the information about the service itself, as a service is obviously using itself, and it will then get the list of active dependent services. Let's do a brief reminder about dependent services. We can say that the service depends on one or more services when it needs those services to be running prior the service can start itself. And it is defined with a value in the registry hive of the service. So let's take an example with the task scheduler, which name is schedule. We can see that there's a line, dependent service, and we can see that the task schedule depends on 2 services, RPCSS and System Events Broker, meaning that it will need those 2 services to be up and running to be able to start. So with this example, let's see what the restart manager tells us about the System Events Broker service. Using a custom tool, we're going to register using the name of the service, this specific service, and see what the restart manager tells us as affected application. When we do enter this name, we can see that the restart manager gives us a list of 2 services, the service itself, as the service is obviously using itself, and also the task scheduler that we've seen is a dependent service on System Events Broker. This way, we know that if something bad, if System Events Broker were to shut down, task scheduler would be impacted. Similarly, for processes, the restart manager will check information about the process itself, because the process is using itself, as we had for services. And if the process is associated with a service, it will retrieve, similarly to what we got before, the list of active dependent services. Let's get the same example, but using it a bit differently. Instead of registering the service System Events Broker, we're going to register here the process that is making System Events Broker running. So for those who had a good memory, the process ID was 728, so we registered this process with the PID. And let's look at the list of applications using it. We can see that there are all the services that are associated with the process, so including System Events Broker, but also all of the other services running with the same process. And we can see at the bottom of the list that Task Scheduler is still here, as Task Scheduler still depends on System Events Broker. So now let's see when an application wants to get rid of the affected applications, how ARM shutdown will process to request the demand. So it depends on the nature of the target application. And the first scenario case is when the affected application is a graphic window. The restart manager, in that case, will send a first message called WM query and session using the function sendMessageTimeout. And this message is a first request to the process asking, hey, are you ready to end? In that case, if the process is ready to end and returns true, well, it's all good. And then the restart manager sends a second message, WM session, that signifies the end of the session. This is not a request anymore. It tells that now the application can be terminated anytime. And if the application is not ready, returning false, then the behavior will depend on how the shutdown has been required. ARM shutdown takes as an argument a parameter called forced shutdown, and if the shutdown is forced, whether or not the application is ready to end, the restart manager will process to the second message with WM end session, signifying whether or not the application is ready to end. Do whatever you need to do, this is going to end. So for notepad.exe, this would be the time where Notepad has a delay to ask the user if he wants to save the data, that type of last-minute operations. And if the application is not ready and that the shutdown is not forced, then the whole operation of the shutdown is cancelled. And then it gives a delay to the applications to close, and if the application is still not compliant, the restart manager will process to a third call to send message timeout with the message WM close, which is equivalent to the red cross on the top of the window saying, okay, end of the story, now you are ending. Now when we have a console window, console windows are not designed to handle that type of message, so the restart manager has to adjust, and we will send what we call a notification, the Control-C event, which is the equivalent of the shortcut Control-C. And this is handled by a control handler that is by default calling exit process, ending the process. We also have the scenario when a process is associated with a service. This way, the restart manager will properly use the service control API and using control service, ask for the stoppage of the service. And regardless of whether the service is stopping or not, we'll use terminate process to terminate the process associated with the service. And lastly, we have a corner case scenario for when the affected application is explorer.exe. Indeed, it will first send the message WM query and session, asking explorer.exe, hey, you ready to end? Then we have the same scenario, whether or not explorer.exe depends yes or returns true or false to this message, and depending on the way the shutdown has been requested, we'll have the second message, WM session, signifying the end of the session. But this time, unlike for graphic classic application, there won't be a call to send message timeout with the message WM close. So when I first saw that, I was wondering, like, why can't we send WM close to explorer.exe? And I figured that when you do send WM close to a session that does not have an explorer.exe window active, so you don't have any file explorer open in your session, you would get this pop-up that asks you, hey, do you want to shut down the system? And since the restart manager whole goal is to avoid the shutdown, of course, this is not what we want. I believe the explorer.exe was historically associated with the session and that Microsoft had to adjust to make sure that the user cannot, unfortunately, reboot the system while it shouldn't. And Microsoft had to adjust that to this corner case, getting a whole dedicated function for the shutdown when the affected application is explorer.exe. So now we know how it works. Let's see who is using that. The typical use case for the restart manager is for installers and updaters, as they will need, before their operation, to A, make sure that they will be able to complete the operation, since they can't afford to be interrupted and to have like an update half done, but they have to do it again after. But also to avoid a reboot in the cases where one application is blocking the files that need to be updated, and that if the application can be shut down, instead of doing a whole reboot, be able to do that. So we're going to try to catch our real case scenario, and to do that, we're going to use the software Ninite That is a software where you can select a bunch of applications that you want to install or update at the same time to save you some time. To monitor how these installers will do, we're going to use the tool API Monitor, and we're going to first set up some functions to hook. So we're going to list all of the functions of the Restart Manager. On the list, we can see some of the core functions that we detailed earlier, but we can see some other functions that will add features to those. Then we're going to launch the 9.8 installer, and we're going to see that there are already some installers that were running. And we can see, using the tool, that the Visual Studio Code installer performed 4 different calls to the Restart Manager functions, starting with the start session, registering them, then retrieving the list with arm getList, and ending the session with arm end session. What we're really interested in is the list of resources that the installer was interested to check. So we can click on ARM registered resources, and we can see the list of files that have been registered within the session. We can see it begins with an executable, and that we can see also all of the DLLs that the installer probably needed to use and wanted to make sure that no other process would block them. We can see also that using all of those arguments and the calls that were monitored, that the installer did not require the shutdown of a function, of any process, as it did not use the ARM shutdown function. But if there were processes blocking resources, it could have used the ARM shutdown function and terminate the applications that were blocking its resources. So if an installer can do that, what can prevent malicious authors from using the Restart Manager to do the same? So we're going to see that indeed, malicious authors have used that in the past, and the first case scenario where it was done was to support the ransomware encryption. The Conti ransomware is a good example, as its source code has been leaked in March 2022. So we're going to look at the code to see how it was used and to exactly what purposes. Their goal was to check, prior to encrypting a target file, that no other process in the system would prevent them from doing so, and this way optimize the number of damage made for one victim, optimizing the number of files that will be encrypted. And to do that, they iterate over all the files of a system, register each potential target in a Restart Manager session, and if there were any affected applications, attempted to terminate them. They implement this in a function called killFileOwner that was taking as argument a file path and file name. The first step was to create a session, so using start session, ARM start session that we know now. The second step, they registered the target file, so we can see this number indicates that only one resource will be registered. They give the name and the path of the file, and all of the other arguments here correspond to processes and services to register in the session. So we can see here that they were only interested about the files, which makes sense as ransomware encrypts files. Then they perform a first call to ARM getList to retrieve the number of affected application. With this number, they allocate the correct structure that will receive the information, which is a Restart Manager structure called ARM process information. And they perform a second call to ARM getList to this time retrieve the actual information about the affected applications. Afterwards, they process this information and they checked that the affected application, so the application blocking a potential file to encrypt, wasn't the process itself, because it'd be too bad to end the ransomware itself, nor any of the Windows processes that couldn't be terminated anyway. And if it was checking all the box, they were used ARM shutdown, forcing the shutdown with this argument of those affected applications. This way, they could get rid of applications that were preventing them from encrypting files and successfully perform their malicious purposes. But that's not it. The Restart Manager can also be used to perform anti-analysis and evasion purposes. But to understand how, we first need to understand how the restart manager can be used to identify running processes. So let's say we have a system. We have binaries that can or cannot launch processes. And let's say we have two binaries, process A.exe, from which process A is currently running, and a process B.exe, which the process is not running, and we just have one binary. If we register those two binaries in a restart manager session, so we're going to send the files, not the processes. It's really important to understand. It's just the binary file. The restart manager will process the information and tells us that process A.exe is currently blocked by process A, since the process is executing from its binary. But for process B, of course, it's all good, as process B is not executing. No process is currently blocking process B.exe. So if we do this operation with all the binaries of the system, we can then retrieve the list of all the processes currently executing. And we can wonder, what can we do with that? Because we get the list, so how can we use it? Well, we can first use it to perform process discovery. So as a first step for reconnaissance purposes, gathering information about what are executing processes and running services will give information about the context of the execution and can help perform other steps later on. But we can also do sandbox or debugger evasions. Once we get the list of applications currently running, we can determine which ones might be sandboxes or debuggers, and so on and so forth. And the malware will then be able to adjust its behavior, so hiding certain functionalities to make sure that it's not detecting or just completely exiting, as if it's monitored, was the point of executing sometimes. And it's currently referred under the MITRE norm as evasion for sandbox and debuggers. We can also do anti-analysis, because once we identify what is the type of processes running in the system, the malware can say, hey, this monitoring tool, I'd rather not see it running, and then attempt to terminate it using RM shutdown. And it is referred as the impaired defense. So now it's time for a demo to see how it really works. So we got a Windows 11 updated. Let's open a CMD. So this is the tool that we've observed right before. So we have a bunch of functionalities, which are the basic registering a file, a process, or service in the Windows Restart Manager session to retrieve the list of affected applications. But what we're really interested in today is to search for the existence of a process running in the system. And we're going to use the example of Process Hacker to see how we can do that. So when we do register it, we're going to use the method that we detailed right before. We're going to iterate over the binaries of the system, so starting from the root. And for all the binaries that we can find, we can see the iteration here. We're going to check for the .executable file if a process is currently blocking them. So here we can see that we entered the repository of Process Hacker, that we successfully identified the .executable. It's so that it is currently blocked by Process Hacker that is executing on the machine, and we can now attempt to end the application using RM shutdown. So if we say yes, no problem, and we can get rid of a Process Hacker that we do not want to see on the system. This has the advantage that the Restart Manager relies on friendly names, user-friendly names of applications, which is by default the file description of the binary. So this technique would work even if your executable is renamed. So if you have a debugger that you want to hide from the Restart Manager, you want to rename it to avoid this, this wouldn't work, as the Restart Manager, when there is a user-friendly name existing, will rely on that. So even with renamed executable, this would work. Before coming back to the slides, there is another use case that I'd like to show. Let's open Process Hacker again. And let's see what happens with Explorer.exe, as it seemed it was a corner case for Microsoft. And let's register using the PID of Explorer.exe. Explorer.exe. So when we do enter it, the Restart Manager sees that the process is using itself as we detailed earlier. And if when we do try to terminate it, it successfully does, and we enter a state where we do not have explorer.exe anymore. But unlike a terminate process, where explorer.exe would automatically restart to not numb the system and numb the user, here we just end up with a black session and no explorer.exe to help us. So this way, our malicious author can, at the end of whatever malicious activity he does, let the user panicking even more with that type of tricks. So fortunately, malicious authors cannot do that with Windows processes or processes that are essentials for the system. So let's see what makes applications immune against that. Well, for applications that are associated with processes, for the really important processes of the system, protected process and protected process light will prevent them from getting shut down this way. So protected process and protected process lights are processes associated with binaries that comply with signature requirements, showing that they're trustworthy. And it's actually defined by an attribute in their eProcess structure that will give them extra protections, and that will protect them against code injection, memory tampering, and trivial process termination, as it's going to limit the accesses that will be granted to that process. So this way, malicious processes that would attempt to use ARM shutdown to terminate processes of the system, if the process is really important for Windows and running as a protected process, the accesses to terminate the process using the resource manager won't be granted to the malicious process. For other processes that are not associated with services, what will protect them will be the user interface privilege isolation barrier. It's a boundary between applications that rely on the integrity level. Processes run with a certain integrity level that is from 0, low integrity, to 4, system integrity, and it will prevent applications running with a lower privilege from sending messages to more privileged applications. So as we've seen that the restart manager relies on the messages wquery end session, wend session, and wm close, it will prevent them from just sending messages and be able to use the restart manager to end them. So to conclude, we have seen more information about the internals of the tool and how it worked under the hood. The restart manager was doing to retrieve the information about processes blocking a given resource. We've seen how it can attempt to terminate applications. We've seen that using the restart manager, it provides techniques that are little known or new to perform process discovery, evasion, and impair defense without using the classic enumeration of processes or terminate process, and to allow you to interact with the restart manager and to be able to see what can and cannot be done with it. I released the tool on my GitHub under the name The Restarter to be able to allow you to use the tool that we demoed earlier and have as much fun as I had with that. And if you have any question, I'll be happy to answer them. If you can raise your hand to facilitate the work of people helping. Well, great. I think we're on time. So we're good? I'll still be around if any. Oh, there's one.
Question? Oh, yeah, one.
Sorry.
Stop the issue with like something reserving a file.
Sorry, can you repeat a bit with the mic? I'm sorry.
Yeah, sorry about that. Back on the permissions for opening a file without sharing reads, are restarts the only real way to override that kind of thing, or can the process not say, "Hey, I want to ignore that someone opened up that opened up a file with read-only on mine"?
It's going to depend on the nature of the process that has the locks and what, the way it has been opened. But in the general case, the restart is indeed the most straightforward way to do, as it's what is currently done in updates when your system asks you to restart the system. So it's the restart is the most forward way to do that.
Right, thank you.
Sure.
Any other questions?
Okay, thanks everyone.
Thanks for attention.